A solar flare is a sudden flash of brightness observed near the Sun's surface. It involves a very broad spectrum of emissions, requiring an energy release of up to 6 times 10^25 joules of energy. Flares are often, but not always, accompanied by a spectacular coronal mass ejection. The flare ejects clouds of electrons, ions, and atoms through the corona of the Sun into space. These clouds typically reach Earth a day or two after the event. The term is also used to refer to similar phenomena in other stars, where the term stellar flare applies. Solar flares affect all layers of the solar atmosphere, when the plasma medium is heated to tens of millions of Kelvin, while the cosmic ray-like electrons, protons, and heavier ions are accelerated to near the speed of light. They produce radiation across the electromagnetic spectrum at all wavelengths, from radio waves to gamma rays. Although most of the energy is spread over frequencies outside the visual range, and for this reason the majority of the flares are not visible to the naked eye and must be observed with special instruments. Flares occur in active regions around sunspots, where intense magnetic fields penetrate the photosphere to link the corona to the solar interior. Flares are powered by the sudden release of magnetic energy stored in the corona. The same energy releases may produce coronal mass ejections, although the relation between CMEs and flares is still not well established. X-rays and UV radiation emitted by solar flares can affect Earth's ionosphere and disrupt long-range radio communications. Direct radio emission at decimetric wavelengths may disturb the operation of radars and other devices that use those frequencies. Solar flares were first observed on the Sun by Richard Christopher Carrington and independently by Richard Hodgson in 1859 as localized visible brightenings of small areas within a sunspot group. Stellar flares can be inferred by looking at the light curves produced from the telescope or satellite data of a variety of other stars. The frequency of occurrence of solar flares varies from several per day when the Sun is particularly active to less than one every week when the Sun is quiet, following the 11-year cycle. Large flares are less frequent than smaller ones. On July 23, 2012, a massive, and potentially damaging, solar superstorm barely missed Earth, according to NASA. According to NASA, there may be as much as a 12% chance of a similar event occurring between 2012 and 2022. Although because this particular figure was based on an extreme extrapolation of the calculated frequency of future storms, the actual probability of this is almost certainly rather lower than 12%. Cause: flares occur when sped-up charged particles, mainly electrons, interact with the plasma medium. Scientific research suggests that the phenomenon of magnetic reconnection leads to this copious acceleration of charged particles. On the Sun, magnetic reconnection may happen on solar arcades, a series of closely occurring loops of magnetic lines of force. These lines of force quickly reconnect into a low arcade of loops, leaving a helix of magnetic field unconnected to the rest of the arcade. The sudden release of energy in this reconnection is the origin of the particle acceleration. The unconnected magnetic helical field and the material that it contains may violently expand outwards, forming a coronal mass ejection. This also explains why solar flares typically erupt from what are known as the active regions on the Sun, where magnetic fields are much stronger on average. Although there is a general agreement on the flare's causes, the details are still not well known. It is not clear how the magnetic energy is transformed into the particle kinetic energy, nor is it known how the particles are accelerated to energies as high as 10 MeV and beyond. There are also some inconsistencies regarding the total number of accelerated particles, which sometimes seems to be greater than the total number in the coronal loop. Scientists are unable to forecast flares, even to this day. Classification: solar flares are classified as A, B, C, M or X according to the peak flux of 100 to 800 picometer X-rays near Earth, as measured on the GOES spacecraft. Within a class there is a linear scale from 1 to 9, n, so an X2 flare is twice as powerful as an X1 flare, and is 4 times more powerful than an M5 flare. H-alpha classification. An earlier flare classification is based on H-alpha spectral observations. The scheme uses both the intensity and emitting surface. The classification in intensity is qualitative, referring to the flares as ain't, normal or brilliant. The emitting surface is measured in terms of millionths of the hemisphere and is described below. A flare then is classified taking S, or a number that represents its size, and a letter that represents its peak intensity, V, G. Sn is a normal sun flare. Hazards. Solar flares strongly influence the local space weather in the vicinity of the Earth. They can produce streams of highly energetic particles in the solar wind, known as a solar proton event. These particles can impact the Earth's magnetosphere, and present radiation hazards to spacecraft and astronauts. Additionally, massive solar flares are sometimes accompanied by coronal mass ejections, which can trigger geomagnetic storms that have been known to disable satellites and knock out terrestrial electric power grids for extended periods of time. The soft X-ray flux of X-class flares increases the ionization of the upper atmosphere, which can interfere with shortwave radio communication and can heat the outer atmosphere and thus increase the drag on low-orbiting satellites, leading to orbital decay. Energetic particles in the magnetosphere contribute to the aurora borealis and aurora australis. Energy in the form of hard X-rays can be damaging to spacecraft electronics and are generally the result of large plasma ejection in the upper chromosphere. The radiation risks posed by solar flares are a major concern in discussions of a manned mission to Mars, the Moon, or other planets. Energetic protons can pass through the human body, causing biochemical damage, presenting a hazard to astronauts during interplanetary travel. Some kind of physical or magnetic shielding would be required to protect the astronauts. Most proton storms take at least 2 hours from the time of visual detection to reach Earth's orbit. A solar flare on January 20, 2005 released the highest concentration of protons ever directly measured, giving astronauts as little as 15 minutes to reach shelter. Observations. Flares produce radiation across the electromagnetic spectrum, although with different intensity. They are not very intense at white light, but they can be very bright at particular atomic lines. They normally produce bremsstrahlung in X-rays and synchrotron radiation in radio. History. Optical observations. Richard Carrington observed a flare for the first time on 1 September 1859, projecting the image produced by an optical telescope, without filters. It was an extraordinarily intense white light flare. Since flares produce copious amounts of radiation at H-alpha, adding a narrow passband filter centered at this wavelength to the optical telescope allows the observation of not very bright flares with small telescopes. For years H-alpha was the main, if not the only, source of information about solar flares. Other passband filters are also used. Radio observations. During World War II, on 25 and 26 February 1942, British radar operators observed radiation that Stanley Hay interpreted as solar emission. Their discovery did not go public until the end of the conflict. The same year Southworth also observed the Sun in radio, but as with Hay, his observations were only known after 1945. In 1943 Grote-Reber was the first to report radio astronomical observations of the Sun at 160 MHz. The fast development of radio astronomy revealed new peculiarities of the solar activity, like storms and bursts related to the flares. Today ground-based radio telescopes observe the Sun from 15 MHz up to 400 GHz. Space telescopes. Since the beginning of space exploration, telescopes have been sent to space, where they work at wavelengths shorter than UV, which are completely absorbed by the atmosphere, and where flares may be very bright. Since the 1970s, the GOES series of satellites observed the Sun in soft X-rays, and their observations became the standard measure of flares, diminishing the importance of the H-alpha classification. Hard X-rays were observed by many different instruments, the most important today being the Reuven-Ramatai high-energy solar spectroscopic imager. Nonetheless, UV observations are today the stars of solar imaging, with their incredible fine details that reveal the complexity of the solar corona. Spacecraft may also bring radio detectors at extremely long wavelengths that cannot propagate through the ionosphere. Optical telescopes. Big Bear Solar Observatory, located in Big Bear Lake, California and operated by the New Jersey Institute of Technology, is a solar-dedicated observatory with different instruments, and has a huge databank of full-disk H-alpha images. Swedish 1M Solar Telescope, operated by the Institute for Solar Physics, is located in the Observatorio del Roque de los Muchachos on the island of La Palma. McMath Pierce Solar Telescope, located at Kitt Peak National Observatory in Arizona, USA, is the world's largest solar telescope. Radio telescopes. Nankai radioheliography is an interferometer composed of 48 antennas observing at meter-decimeter wavelengths. The radioheliography is installed at the Nankai Radio Observatory. Owens Valley Solar Array is a radio interferometer operated by New Jersey Institute of Technology, consisting of 7 antennas observing from 1 to 18 GHz, in both left and right circular polarization. OVSA is located in Owens Valley, California. It is now being improved, increasing to 15 the total number of antennas and upgrading its control system. Nobiyama Radio Heliograph is an interferometer installed at the Nobiyama Radio Observatory, formed by 84 small antennas, with receivers at 17 GHz and 34 GHz operating simultaneously. It continuously observes the Sun, producing daily snapshots. Siberian Solar Radio Telescope is a special-purpose solar radio telescope designed for studying solar activity in the microwave range, where the processes occurring in the solar corona are accessible to observation over the entire solar disk. It is a crossed interferometer, consisting of 2 arrays of 128 by 128 parabolic antennas 2.5 meters in diameter each, spaced equidistantly at 4.9 meters and oriented in the EW and NS directions. It is located in a wooded picturesque valley separating 2 mountain ridges of the eastern Sayan Mountains and Karmadeban, 220 kilometers from Irkutsk. Daily solar images are available. Nobiyama radio polarimeters are a set of radio telescopes installed at the Nobiyama Radio Observatory that continuously observes the full Sun at the frequencies of 1, 2, 3.75, 9.4, 17, 35, and 80 GHz, at left and right circular polarization. Solar Submillimeter Telescope is a single-dish telescope that observes continuously the Sun at 212 and 405 GHz. It is installed at Complejo Astronómico El Leoncito in Argentina. It has a focal array composed by 4 beams at 212 GHz and 2 at 405 GHz. Therefore, it can instantaneously locate the position of the emitting source. SST is the only solar submillimeter telescope currently in operation. Polarization emission of millimeter activity at the Sun is a system of 2 circular polarization solar radio telescopes for observations of the Sun at 45 and 90 GHz. The novel characteristic of these instruments is the capability to measure circular right and left-hand polarizations at these high frequencies. The system is installed at Complejo Astronómico El Leoncito in Argentina. It started operations in November 2011. In November 2013 it went offline for repairs. It is expected to return to observing in January 2015. Blian Radio Observatory is a set of radio telescopes operating near Greenwich. They continuously observe the solar flare radio emission from 10 MHz to 5 GHz. The broadband spectrometers are known as Phoenix and Callisto. Space telescopes. The following spacecraft missions have flares as their main observation target. Yuko. The Yuko spacecraft observed the Sun with a variety of instruments from its launch in 1991 until its failure in 2001. The observations spanned a period from one solar maximum to the next. Two instruments of particular use for flare observations were the soft X-ray telescope, a glancing incidence low-energy X-ray telescope for photon energies of order 1 keV, and the hard X-ray telescope, a collimation counting instrument which produced images in higher energy X-rays by image synthesis. Wind. The WIND spacecraft is devoted to the study of the interplanetary medium. Since the solar wind is its main driver, solar flares' effects can be traced with the instruments aboard WIND. Some of the WIND experiments are a very low-frequency spectrometer, particles detectors and a magnetometer. GOES. The GOES spacecraft are satellites in geostationary orbits around the Earth that have measured the soft X-ray flux from the Sun since the mid-1970s. Following the use of similar instruments on the SOLRAD satellites, GOES X-ray observations are commonly used to classify flares, with A, B, C, M, and X representing different powers of 10. An X-class flare has a peak 128A flux above 0.0001 W per square meter. RHESSI. The Reuven-Ramatai high-energy solar spectral imager is designed to image solar flares in energetic photons from soft X-rays to gamma rays, and to provide high-resolution spectroscopy up to gamma-ray energies of ~20 MeV. Furthermore, it has the capability to perform spatially resolved spectroscopy with high spectral resolution. SOHO. The Solar and Heliospheric Observatory is collaboration between the ESA and NASA which is in operation since December 1995. It carries 12 different instruments, among them the Extreme Ultraviolet Imaging Telescope, the Large Angle and Spectrometric Coronagraph and the Michelson Doppler Imager. SOHO is in a halo orbit around the Earth-Sun L1 point. TRACE. The Transition Region and Coronal Explorer is a NASA Small Explorer program to image the solar corona and transition region at high angular and temporal resolution. It has passband filters at 173A, 195A, 284A, 1600A with a spatial resolution of 0.5 arcsec, the best at these wavelengths. SDO. The Solar Dynamics Observatory is a NASA project composed of 3 different instruments: the helioseismic and magnetic imager, the atmospheric imaging assembly and the extreme ultraviolet variability experiment. It has been operating since February 2010 in a geosynchronous Earth orbit. Hinode. The Hinode spacecraft, originally called Solar B, was launched by the Japan Aerospace Exploration Agency in September 2006 to observe solar flares in more precise detail. Its instrumentation, supplied by an international collaboration including Norway, the UK, the US, and Africa, focuses on the powerful magnetic fields thought to be the source of solar flares. Such studies shed light on the causes of this activity, possibly helping to forecast future flares and thus minimize their dangerous effects on satellites and astronauts. ACE. The Advanced Composition Explorer was launched in 1997 into a halo orbit around the Earth-Sun L1 point. It carries spectrometers, magnetometers and charged particle detectors to analyze the solar wind. The real-time solar wind beacon is continually monitored by a network of NOAA-sponsored ground stations to provide early warning of Earth-bound CMEs. MAVEN. The Mars Atmosphere and Volatile Evolution mission, which launched from Cape Canaveral Air Force Station on November 18, 2013, is the first mission devoted to understanding the Martian upper atmosphere. The goal of MAVEN is to determine the role that loss of atmospheric gas to space played in changing the Martian climate through time. The Extreme Ultraviolet Monitor on MAVEN is part of the Langmuir Probe and Waves instrument and measures solar EUV input and variability and wave heating of the Martian upper atmosphere. Examples of large solar flares. The most powerful flare ever observed was the first one to be observed on September 1, 1859, and was reported by British astronomer Richard Carrington and independently by an observer named Richard Hodgson. The event is named the Solar Storm of 1859, or the Carrington event. The flare was visible to a naked eye, and produced stunning auroras down to tropical latitudes such as Cuba or Hawaii, and set telegraph systems on fire. The flare left a trace in Greenland ice in the form of nitrates and beryllium-10, which allow its strength to be measured today. Cliver and Svalbard reconstructed the effects of this flare and compared with other events of the last 150 years. In their words, while the 1859 event has close rivals or superiors in each of the above categories of space weather activity, it is the only documented event of the last 150 years that appears at or near the top of all of the lists. In modern times, the largest solar flare measured with instruments occurred on November 4, 2003. This event saturated the GOES detectors, and because of this its classification is only approximate. Initially, extrapolating the GOES curve, it was estimated to be X28. Later analysis of the ionospheric effects suggested increasing this estimate to X45. This event produced the first clear evidence of a new spectral component above 100 GHz. Other large solar flares also occurred on April 2, 2001, October 28, 2003, September 7, 2005, February 17, 2011, August 9, 2011, March 7, 2012, July 6, 2012. On July 6, 2012, a solar storm hit just after midnight UK time, when an by 1.1 solar flare fired out of the AR 1515 sunspot. Another by 1.4 solar flare from our 1520 region of the Sun, second in the wick, reached the Earth on July 15. 2012 with a geomagnetic storm of G1, G2 level. AX1.8-CLASS flare was recorded on October 24, 2012. There has been major solar flare activity in early 2013, notably within a 48-hour period starting on May 12, 2013. A total of 4 X-class solar flares were emitted ranging from an by 1.2 and upwards of an by 3.2, the latter of which was one of the largest year 2013 flares. Departing sunspot complex AR2035 AR2046 erupted on April 25, 2014 at 0032 UT, producing a strong X1.3-CLASS solar flare and an HF communications blackout on the day side of Earth. NASA's Solar Dynamics Observatory recorded a flash of extreme ultraviolet radiation from the explosion. In early November 2015, solar flares disrupted the air traffic control system in central and southern Sweden, causing heavy delays for passengers.